Hello, hello, and we are live. Sorry, it took me a little bit longer to actually start streaming, like get all set up and stuff than I wanted it to, but we're live, and that's what matters. Let's see, what are the vibes of this music mix? It'll work. Actually, I do want to change the vibes off. I mean, what do we think the chances of the epic Commodore 64 SMT collection for being used in copyright system? And is that a risk that there might be? Let me just double check that I am recording the stream. Okay, yes. I will turn that down. Oh, I have application capture and desktop capture on. Let's turn off application capture. Right about there should be good. Maybe music slightly higher? There we go. It is good music. It's probably more soothing than my voice. I actually meant to... Eventually I'm gonna swap out the world music for this world that I'm in right now with the with this actual video, which is like 10 hours of Commodore 64 music. Which, this is the vibe. Surprised I'm not at the FIA rave event. I was thinking about it, but I really want to get this part of the engine working, and spent the rest of today, or the part of today that has already elapsed, working. Did I bring my water bowl upstairs? I did not. I'm gonna need to walk down and grab that eventually. But I spent the rest of the day working on other job, so I'm like, I very much want to get back to this, and I can show you the state that we're currently in, which is BraneScript is technically working, but it's not. Like, technically, we go through all of the steps, we parse out the text, we generate an intermediate representation, and then that intermediate representation is turned fully into JIT-compiled bytecode. And then we actually run that, which is what we're about to do here. Any second now. It does take a bit to load up. There we go. And then once it finally loads, it runs instantly. But this is what the debug currently looks like. So I'll kind of blow that up a little bit. But yeah, so what's going on? Let me see if I can get the sizing on this to work so I can show everything at once in one frame. So what's going on is first we compile the module, we go through all the compilation steps. After this point here, we have like fully compiled the functions, they're loaded, and like ready to be run. So when this says was able to load function, these are the two functions that make up a pipeline stage. So behind the scenes, pipelines are still technically functions, but we just abstract over that in like the language of the grammar and how the actual intermediate representation works and whatnot. And then after we've loaded those functions, I create like a very simple test environment. So to actually run scripts, we need a couple different things. The thing that makes memory actually secure, make it so that we can't access memory outside of our virtualized environment, is this bindings page. So this is a list of, I don't know if I'm going to keep it this big, I might crop it down by a couple factors of 2, but this bindings page holds an array of pointers. And then this memory page here is an example of memory that we could bind to any of our scripts. And basically just simplifying all that down, this buffer here is the only memory that we want our script to be able to access. Like, we want it to be physically unable to access any memory except the memory that we explicitly give it access to. So we take this binding page, we also allocate a memory page, and then we run a for loop over all of the memory in this memory page, initialize that to 0, so we just have a starting point of clean memory. And then we iterate over every single member of the bindings page, and we just set that to be a pointer to the memory page. So the way that I want like the memory binding system to work is that all of these bindings, except for index 0, can be rebound. So if we want to give scripts access to more memory, we just change one of these pointers in this initial buffer to another allocated bit of memory that we're like, okay, I want the script to be able to access this too. So that's how that works. But if they haven't been bound to anything, we don't want the script to be able to access like a random memory address and then just like undefined behavior. We don't want that to happen. So we just preset every single member of that array to just that initial memory page. That way, if a script tries to be malicious and access outside of what they know is bound, they just get the same exact like default memory page. So the script will definitely like not do what it's expecting to do, but it won't crash anything and it won't get any like information that it wasn't expecting to have. Next, what I do is all of these functions don't accept or return anything more than like 3 integers, so I'm just using one structure for all arguments and return values. And these functions also don't have actual return values. The way I decided to end up doing function calls is, I can actually show it to you here. If we actually look at, not JIT pipeline, I'm gonna look at JIT function handle. So this is the signature that we're using for functions currently. And eventually it might actually just be like straight up nothing, or just only one integer pointer. So this is the pointer to our array of memory. So that's all the bindings that we need. And then this here is a Brane script pointer, the int form of a Brane script pointer, which is, the first one is the binding to access, and the second is the index within that binding. So basically it's just telling it how to get it out of this pointer. So this pointer is like your input struct, so this is a pointer to an input struct within that bound slice of memory. and then this second pointer is where we want the output struct to be. Now, I got this so close to working. Like, it was giving me the correct output, but it was overriding, like, the 0 position. And then, like, I fixed some bugs, and then it stopped working altogether. I know that the bugs were fixed, but the fixing the bugs also fixed it almost working. So now, we just get this, where these little bits of... You can ignore these bits here it's setting. Those are, like, debug values, where I'm just having it, like, every time it accesses a pointer, it's writing out the offset that it tried to use. So this would be, like, 12, 12, and 24, and I just added that to 100, so I could, like, if it's 100, that's 0. So I'm even able to tell, like, if that part of it was working, because I wasn't even able to tell if the pointer offsets were working initially, because they were all 0, and I couldn't tell the zeros, like, I couldn't tell the difference between the zeros and the memory that just hadn't been set, like here, that hasn't been touched at all. With these 52s, I have no clue what's going on there. Every single rendition of this function of F2 printed out like 4 negative 52s in a row. Initially it was here, then I fixed stuff, and it ended up being here, which is where the output struct is supposed to be. So, yeah, I don't know what's going on there. But what we are doing to try to fix all of this is right now, I was like very wishy-washy on how I wanted to handle the stack, like, stack versus heap memory. Like, I didn't want to just use our included memory as the stack, the way Wasm does. So with Wasm, it doesn't use the actual stack of the host environment, which is what I kind of wanted to try to do. Instead, it uses bound memory as its stack and also as its heap. So it has its own allocator, etc. And it would just use the memory it's provided with. But I was like, I want to try using virtual registers sort of deal, and then have that automatically be put on the stack, or like optimized out by LLVM. And because the LLVM memory to register optimization pass needs everything defined on, like, every variable defined in the first basic block, so basically the entry of the function, you need to allocate all of your memory there instead of afterwards when any branching might have occurred. So we'll put this into the intermediate representation. We'll just redefine everything we need. Now, some of these we don't actually end up using, and some of these would be much better as just like register values. But like, since the intermediate representation, I didn't want to actually write a register allocator, because that is absolute torture. I ended up basically just putting everything on the stack anyways. Yeah, and like I had a like very large like Discord message I sent in the Discord where it's like essentially what I'm saying now, but I basically decided instead of doing this pseudo register based thing that I'm doing now, since I'm already passing input in on the bound memory, like I'm already doing that. Like function calls already happen in the way the stack machines do it. And yeah, like it's already very like stack machine oriented. So the solution is just to like make it fully a stack machine. Get rid of all of these virtual, get rid of all the virtual registers and just fully copy the Wasm, like, intermediate representation. Not, like, fully, because I want to have better debug information than the Wasm spec does, because the WASM spec doesn't include debug information. The best that they do for debug information is, oh, we'll let you put comments in there. Generic data. Now you get to do how the debug information however you want, instead of taking the opportunity to be like, hey, here's a good debug information. Good developer experience. You can actually figure out what's going on. No, they were like, no debug information, put it in the comments. So I definitely want debug information in my intermediate representation, and that's basically what I'm going to add after I get basic language features in. That's like after I get it running well and get like a fair number of extra stuff in there. That's like debug information is the next step. Theoretically, we should even be able to possibly step through debug this. Like I can step into the assembly code and see what this has actually been compiled to. But yeah, debug information is important, and we're completely ignoring it right now, but won't ignore it at all in the future. Well, we are getting rid of all of these. So I had a realization, which is that stack machines basically have these values implicitly. I can write this in such a way that I never have to write a stack machine interpreter, and none of the JIT backends need to actually implement it as a stack machine, except for that being the calling convention of functions. I straight up just don't have to make an actual stack machine, which was my main... I didn't want to make a stack machine because I don't see them as performant. You want to use registers. You don't want to the stack memory is the fastest memory out of any memory type, but registers are even faster, and caches and whatnot. But I realized oh, instead of having to do this whole deal where we define types ahead of time and very much could you imagine how big this would be for a huge function? There could be hundreds of these, because I'm even allocating these for temporary values and return values and all sorts of stuff we don't need to have here. In fact, half of these commands are completely unnecessary if I was... Well, actually, no. Half of the intermediate representation for this command, well, the majority of the intermediate representation for that command isn't necessary if I do a, if I just do a stack machine based representation. But yeah, so that's kind of where I'm at. And what we're going to be doing on this stream is getting as far as we can into converting RIR into the most shameless WASM knockoff, but improved. And we'll get to that right after I go and grab some water, because my voice is not happy. Because the strange thing about streaming is I drink a lot more water on stream than I do normally, because you can, when you talk a lot on stream, you can very much tell in what condition your vocal cords are and how hydrated you are. And I need water. I really need water. went through all the trouble of filling up a water bottle before like I actually even ate dinner, because I'm like, oh, I'm gonna stream after dinner. And then I just forget to bring it up to me, set up the entire stream, and then no water bottle. Just leave it downstairs. But there we go. Now we are set. What? Get my desk set up again. Oop. Apparently I was not centered where I thought I was. One second. There we go. Perfect. Now for the coding to begin. I think the first task is just to go through the intermediate representation and convert it to just, at this point, since I'm doing a stack machine, like, we're going to rely on Wasm even more shamelessly than before. Like, the recentering made it so my monitors are further away from me than I want them to be. I have to use my very constrained hand motions to bring them closer. Alright. And now, certain commands mean different things now. For instance, the load and store operations are completely different. Oh, interesting. Why? Oh, that's like zero extension loading. That's cool. Now, do I want to keep the syntax of type.operation? Or do I want to do it to change it to be operation.type? Because I don't think it makes much sense to have it be... Well, I mean, like, it's very understandable. It's like this is the type that we're doing the operation on. I was wondering how I would represent it. I think I stick with my own system, but just copy the general vibe. So here for... do they have constant? I know in WASM code for like constants and stuff, you can do, it's either load or store. Because this loads bytes off of the stack, and this stores bytes off of the stack. Oh, that's what there's the constant operands. I was wondering where those were. So we're gonna copy this in spirit. Going in order of, what does get and set do? The instruction gets the value of a variable, sets the value of a variable. Wait, what's the difference? Exec space is for locals, is only... refers to the list of locals declared in the current function, including parameters. Wait, what? So wait, WASM has a set of locals as well, like I'm doing already. But so I guess everything on the stack machine is not named variables instead of what I thought it was going to be before, which interesting, because I kind of just assumed that like function arguments are pushed to the stack, and then you just use them off of the stack. That's how a stack machine works, right? Okay, so this creates a local variable named variable. Okay. I'm confused, but why have a different system for locals when you already have the stack and you can just back reference the stack, right? Or can you only... Well, no, you could do like... Memory is accessed with load and store instructions for all the different value types. They all take a memory immediate memr that contains an address offset and the expected alignment. And the expected alignment, the immediate value memory argument align is an alignment hint about the effective address. It is a power of 2. Yeah. If memarg align is incorrect, consider to be misaligned. Misaligned accesses still have some behavior. Aligned access only possible. Okay. Wait a second. So... does WASM not have a way to access other variables on the stack? Like, are we not able to... like... Here, one second, I'm cleaning off my lenses. Oh, much better. Kind of. I might have hair in my actual headset. That might be what's going on. Okay. So yeah, that it doesn't look like WASM really has a way to actually deal with the local stack. Aside from get and set, which technically kind of works like local variables. But then you're dealing with like the overhead of load and store commands, which I mean you have to do anyways. This honestly could still work. YouTube is complaining my bitrate is too low. I think if I up it, it won't nuke Twitch. That holding steady? Like it is. The screen should be a little bit easier to see now. Oh, it's still complaining about the bitrate. That did nothing. I bet it's because the secondary targets need to be restarted. Oh well, we'll just live with it. Okay. Less than, greater than, less equal, greater equal. Question is, do I keep native type? Or do I go full in on this? I still want there to be like some amount of reflection possible in the runtime itself. Like gathering information about structures and whatnot. So it makes sense to retain like struct definitions and whatnot. I think we keep most of the structure the same. I'm just considering, like, do I want to go full in on every single operand here? Like, every single one of them being different per type, and letting types be expressed fully in the operand system? Or do I want to, like, allow there to be arguments to commands? So here on, say, instead of constant I32 or U32 or F32, it would just be constant, and we'd throw a variant in there. Or like IR native type it. I mean, I'm not doing anything with constants yet. Second, I just got a message. Let's see what it means. Okay, I can leave planning for that until later. Call this IR op constant. We're gonna have a variant on the actual type here. And then we'll decide what that looks like in the text representation later. But then that native type thing here is just then represented by the actual constant there. Say IR operation. There isn't a move operation, is there? Yeah, there's only loads and stores, which put together loads and stores do make a move operation. So I guess next we'll do just load operation. Oh dang. We don't need to do destination. Most of these end up being empty structures. Because, like, load operation. Like, you take your pointer off of the stack, and you replace that pointer on the stack with your value. So all load op has to be, if I want to stick with the not making a separate type for every single thing, then all this needs is IR native type, and this is the type to load. And struct member accesses. Do I want to represent struct members? Do I want to represent struct members in the actual intermediate representation or not? So the way that I imagine this working when it's actually being like JITted is it's not actually a stack machine. We just treat it as a pseudo stack machine. So I have an array of like LLVM values. And whenever we like process an intermediate representation, like whenever we process an IR whatever, what we would do is like if we have a move command, that is a W. Not move, let's say add. If we have an add command, we would take the two values off of the stack. These would just be LLVM value pointers. Then we would replace the first one with the results. And that's how we would handle the add operand. But what if I wanted to use these values like over and over again, but they just got consumed by add? Would that be what you use locals for? It seems like maybe. See, this is me, like, mentally over-optimizing again, because I'm thinking here, like, how do I make this not just a straight-up stack machine? Because all of this gets super easy if I do just create a straight-up stack machine. But then I have to represent structures on the actual compiler side, and actually do like all the memory operands on the bytecode side instead of like letting LLVM take care of all of it for me and dealing with like the debug information, all of that for me. But if I keep the structures on the on this end, and then there's like the whole I'm eyeing these local GIN sets. What's local T? Okay, so that's a non-consuming set. I could do that on the compiler side if like needs a memory address or doesn't need a memory address. Like, yeah, will this ever be referenced in such a way that it actually needs a compiler's like a stack value? Because the problem I'm running into right now is... Actually, this isn't too big, now that I'm actually, like, looking at it. But... like, that's a ton of move and stores. Like, this is a single add operation. Like, this code gen is terrible. I mean, the majority of this function is loading everything out of the input structure and then storing everything in the return structure. Like, that's the majority of everything. And then these four instructions here are the actual add operation. And hopefully these load and store operands would be optimized out of by LLVM, which was my like hope there, but I'm not planning on actually writing like a backend for BraneScript for LLVM, like a BraneScript backend for LLVM anytime soon. So then that means we have to do client-side optimizations, which are to be avoided. I guess I just really need to decide how I want memory to work. The structures always need to be defined on the stack, and if a value is mutable, for the most part that should also be on the stack. Mutable values and structures. Right now, all of our values are mutable, so all of them would go on the stack. Yes. A lot of my mental struggle right now has to do with how I want to handle structures. Because with this thing, let's say I have a like function foo, and this all functions in Brane Engine right now, or BraneScript, all of them take in a structure and all of them output a structure. Like, that's just how it works. And the way that I have that currently set up is, like, that structure gets put on the stack somewhere, like virtualized stack, not real stack. And then we pass in a pointer to that structure into the function, and then the function, you also pass in a pointer to where you want the return value to be. So it means you would actually pre-allocate both the input and return values. I don't want that to be how it works, though. The way that it should work is that we have